Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve this beautiful problem. The problem is, let A be the set which satisfies these three following conditions. Condition 1, elements of A are three distinct complex numbers. Condition 2, 0 is not an element of A. In condition 3, if x and y are both elements of A, then xy is also an element of A. Then find this set A. Alright, let's solve this problem. First, we have to introduce some unknown variables to denote three elements of set A. And let's just call them x, y, and z. And considering conditions 1 and 2, suppose that x, y, and z are all distinct and non-zero. And now it's time to play with this third condition. Because of this condition, these are all elements of A. First, xy is an element of A, and similarly, xz and yz are also elements of A. Moreover, x squared is also an element of A, and similarly, so are y squared and z squared. And since x and xy are both elements of A, their product, x squared y, is also an element of A, and the product of x and yz, which is xyz, is also an element of A, and so on. Alright, so we have infinitely many expressions for the elements of A, but where do we go from here? Well, the first condition states that elements of A are three distinct complex numbers, so let us try to find the expressions that are distinct. More specifically, let us focus on these three, x squared, xy, and xz. Here, let us calculate their differences. That is, x squared minus xy gives x times x minus y, and x squared minus xz gives x times x minus z, and xy minus xz gives x times y minus z. Now, do you remember that x, y, and z are all non-zero and distinct? That means that these x minus y, x minus z, and y minus z are all non-zero. Therefore, x times x minus y is non-zero, and this is also non-zero, and this is also non-zero. Therefore, x squared, xy, and xz are all distinct. They're all different numbers, and they are obviously non-zero, so x squared, xy, and xz are three distinct elements of set A. Therefore, we can write set A as not just x, y, and z, but also as x squared, xy, and xz. Now, the obviously wrong step would be simply letting x equals x squared and y equals xy and z equals xz. We cannot do that because these elements are not necessarily ordered in the same manner. So it does not work like this, but what we can say is that because these three elements are distinct, their products must be equal. So we can say x times y times z equals x squared times xy times xz, and this is the reason why I first proved that they are all distinct. So this gives xyz equals x to the power of 4 yz. And since xyz is non-zero, we can divide both sides with xyz to obtain 1 equals x cubed. So we have obtained the condition for x. At this point, you might have noticed that we can basically do the similar process for y and z. Then we also obtain y cubed equals 1 and z cubed equals 1. Now let's ponder on what we've just found out. We have three distinct numbers x, y, and z satisfying x cubed equals 1, y cubed equals 1, and z cubed equals 1. This means that x, y, and z are three distinct roots of the cubic equation t cubed equals 1. And if we solve this equation, first we have t cubed minus 1 equals 0, and if we factor the left-hand side, we have t minus 1, t squared plus t plus 1 equals 0. So we have t equals 1 and minus 1 plus minus square root of 3i over 2. Therefore, elements of set A are 1 minus 1 plus square root of 3i over 2, and minus 1 minus square root of 3i over 2. And this is the set A that we are looking for. Alright, so we have found the answer, but here let us actually check the third condition using the elements of set A we have just obtained. That is, let us actually check that the product of any two elements of set A is also an element of set A. So we have these three numbers. So without loss of generality, let x equals -1 plus square root of 3i over 2, and y as -1 minus square root of 3i over 2, and z as simply 1. Then multiplying with z is pretty obvious, since it is simply multiplying 1. So these are all pretty obvious. So let us think about the product between x's and y's. First, if we multiply x and y, we have this times this. So using this formula, we obtain -1 squared minus square root of 3i squared over 4, which is 1 plus 3 over 4. We obtain 1, which is an element of a. Next, for x squared, we have 1 minus 2 square root of 3i minus 3 over 4. So we have -1 minus square root of 3i over 2, which is y, so it is an element of a. And for y squared, now we have 1 plus 2 square root of 3i minus 3 over 4, so we have -1 plus square root of 3i over 2, which is x, so it is an element of a. We can also check this using the polar form of the complex number. If you have learned about the polar form, you might know that 3 roots of the equation t cubed equals 1 can be expressed as, in polar forms, first 1, then cosine 2 pi over 3 plus I sine 2 pi over 3, and cosine 4 pi over 3 plus I sine 4 pi over 3. And this one is basically just cosine 0 pi over 3 plus I sine 0 pi over 3. And you might know that they are these points on the complex plane. So we can also write A as this, and without loss of generality, let this as x, and this as y, and this as z. As for their products, we use the following property regarding complex multiplication. As you can see, the angles are added. Then we can easily find that xy becomes cosine 2 pi plus I sine 2 pi, which is just 1. And x squared is, if we double the angle, cosine 4 pi over 3 plus I sine 4 pi over 3, which is y. And for y squared, we have cosine 8 pi over 3 plus I sine 8 pi over 3, which is equal to cosine 2 pi over 3 plus I sine 2 pi over 3, which is x. And that's all for today's video. Thank you all for watching, and I will see you in another video.